Hello, everybody. My name is Heye, and I am a project manager for laser development at Class 5 Photonics. We are a company based in Hamburg, and actually we are on the grounds of the German electron synchrotron facility DESY, which I think most of the people know here. We at Class 5 serve the ultrafast laser market with our customized solutions now for more than over 6 years. And today I want to talk about actually two systems, not only one. One is here presented in the title, and both systems are very similar. While one is focusing at higher repetition rates, namely 1 megahertz, and the other one is focusing on higher pulse energy output running at 200 kilohertz. So both are dual channel CEP stable fuse cycle OPCPA systems with outputs around 800 nanometers and 2 micrometers in wavelengths. So let me just jump into the OPCPA design directly here. And yeah, both systems use diode pumped femtosecond industrial lasers with the central wavelengths at 1 micrometer. For the high repetition configuration, we are using a Coherent Monaco, which has a 1 megahertz repetition rate and 60 microjoules of total pulse energy. So 60 watts in total, and comes with sub 300 femtosecond pulse durations. For the high pulse energy configuration, we're using a carbide from light conversion operating at 200 kilohertz with their 40 watt output, so 200 microjoules, and also similar pulse duration of sub 300 femtoseconds, which make the overall OPCPA design very similar because you have the same pump pulse duration, and so it helps you for the dispersion management with just slight adaptations. Yeah, all systems are available with a third optional output. That's a no-brainer where you actually can just feed through the 1 micrometers right through the box and have it as an additional output. The nice thing is the system is fully integrated. The industrial pump laser sits on the same water-cooled breadboard so that the whole box, the OPCPA and the pump laser are sharing the same thermal environment, and that contributes a lot to the long-term stability, which I will show later. In the OPCPA design, we split roughly 30 microjoules into the seeder, where a fraction of the 30 microjoules is used for a standard white light continuum generation, which offers us a blue shifted white light in the typical range, showing here in that figure that covers a range from 550 nanometers up to 1 micrometer. This white light is then used subsequently in a different frequency generation stage where we generate passively a CP stable idler signal by seeding the process with 1030 nanometer seed photons from the pump laser and pumping them with the blue shifted visible continuum of the white light. So that gives us a broadband CP stable or passively CP stable idler spectrum, which is shown here at a 1 megahertz repetition rate, and it spans from 1.5 to over 2.5 micrometers in spectrum. This idler spectrum is then amplified further in a non-collinear OPA process using the remaining 28.5 microjoules of power, resulting in a little bit more narrow, I will show later, but first of all, showing a great stability. Here measured over 14 hours, we reached like 0.21% root mean square power stability in that setup, and a little bit narrow 1.95 centered wavelength spectrum with a nice Gaussian beam profile. That process offers us so much average power already, or pulse energy, and in the next process we use, after bulk compression, we split a part of the light for a second white light process. I will come to that later, but it allows us to offer a dual channel option where basically 50% of the light is redirected out of the box and the user can use it for his experiments. In this special case here, we use fused silica as a bulk compressor, and we reach TUD limited sub 40 femtosecond pulses. I can show also some frog measurements the measured Fock trace in the upper left. We have the reconstructed trace on the lower left side, and we see we have a more or less TOD limited 2 micrometer pulse with a full width half max of 36 femtoseconds. So obviously, if you in that specific system, the customer didn't really need a full compressed pulse. So if you want to get rid of this TOD effects, we would need to add special customized dispersive mirrors to get the full spectrum compressed to a nice pulse at 36 femtoseconds full with half max. But for here, we use this bulk compressed fused silica to start a second white light, which is now pumped around 1.91 to 2 micrometers. And since the driver pulse is CEP stable, all the white light components are also CEP stable in that setup. This white light spans from 1.9 down to 500 nanometers in the spectral range. I can just show a part of it here, measured with one of our spectrometers, which is limited up to 1.1 micrometers. But these CEP stable frequencies can now be further amplified in a second OPA stage. So we use for the first configuration running at 1 megahertz, 30 microjoules from the 60 microjoules and convert them or frequency convert them in a standard SHE stage and pump the following non-collinear OPA, which is seeded with a CEP stable white light with 15 microjoules. In the high pulse energy version, where we operate at 200 kilohertz, we can use the remaining 170 microjoules and pump the NOPR with 90 microjoules, which just allows us to get a nicer and higher pulse energy throughput in this OPA process. And obviously, if you would have a bigger pump, you can also use the same schematic to even reach or pump with on the millijoule levels. Next, I want to show some data for both systems. First, let me start with the high repetition rate configuration. Here we see a long-term power stability, again measured above for more than 14 hours. We reach 0.3% root mean square stability. We have a nice broadband OPCPA wavelength spectrum centered around 800 nanometers and a Gaussian intensity beam profile. After compression of the NOPR stage, we used an F2F interferometer to measure the first passive CEP of the setup, and then also to provide a feedback loop generated by the F2F interferometer that then sends the feedback signal directly to a stage operating in the DFG process. And what we see here on the left side is the signal in the brighter red, where we see the CEP fluctuating, and it's all below 250 millirads. And once the stabilization is on, we reach a root mean square of 174 millirads. For the high pulse energy configuration, we have similar power stability, 0.28% root mean square, here measured over 25 hours. There's basically no change in the setup. We have a nice ellipticity again, around 0.94, where round equals 1. We have the central wavelengths. The spectra are very similar if you compare both systems. And also a good M square value below 1.2. On the right-hand side, you can see the beam caustic, which provides for all positions after the focus, before the focus, the same Gaussian beam profile, and astigmatism-free focusing of the beam. Okay, so last but not least, I want to show some compressed pulses for, in that case, for the higher pulse energy version, and we use the D-cycle from the company D-Sphere, where dispersive material is integrated into the beam. And what you see on the upper left side is a measured spectrum. On the right side it's their algorithm with a retrieval or this descan or decycle trace. And again, similar to a frog evaluation, you get the wavelengths, the spectral phase, and obviously the temporal intensity profile of your beam. What we see here is that most of the power above 75% is in the main peak. We are reaching 8.45 femtoseconds given by the retrieval. And there still are some satellite peaks that this is data we just generated this week. So we need to work a little bit more on the better pulse compression to get more than 95% of the intensity into the main peak. But here, for sure, we already see 8.5 femtoseconds of CEP stable few cycle 800 nanometer pulses coming out of a single box. And yeah, here are some impressions of the real hardware of this dual channel CEP stable few cycle OPCPA operating at 800 nanometers and optionally has a above 1.7 micrometer wavelengths output. Both systems, or the systems, operate either at 1 megahertz or 200 kilohertz, providing roughly 1 microjoule of pulse energy or about 50 microjoules, depending on your experiment. The pulses are passively CEP stable and can be actively controlled. We show sub 9 femtosecond pulses at 800 nanometers and sub 40 femtosecond pulses at 2 microns. So thank you very much for your attention. I hope everybody has a good virtual conference. And if you want to reach out, please don't hesitate to contact us or get in touch with us. And on all the channels, YouTube, LinkedIn, Twitter, or classic emails. Thank you.